Alright, so we'll go ahead and get started. Today, we're going to nearly finish up the story of neutron stars, where up until now, we've really only told you about sort of the general properties and generic features of neutron stars. We delved in a little bit into the idea that there are magnetars, but really need to talk about all the different kinds of classes of objects that we really get as we form these neutron stars at the center of supernova remnants and things. So what we're going to be talking about is exactly that. It's neutron stars do. And so, we did tell you there's this nice generic story of forming these pulsars. They're born spinning fast in supernova remnants. They have these magnetic fields, 10 to the 12th Gauss or so. And they emit these radio pulses, and then we had this nice spectacular example, the Crab Nebula and the pulsar at the center. And we have talked about magnetars, but there's really much more variation than just these two groups. And so here's sort of a list of some of these things, and this sort of what happens with thinking about a neutron star that is technically isolated, so it's just evolving by itself. And what you can get is sort of the normal things that we've been talking about, the rotation-powered pulsars. But then there's these special class of the isolated neutron stars that we actually call isolated neutron stars. We'll talk about what those are. They are actually sort of the least exciting of the group. And then there are anomalous X-ray pulsars and soft gamma ray repeaters. You'll see that those two are very similar to each other and may in fact be sort of different sides of the same coin, so to speak, or at least different evolutionary stages perhaps of the same object. And there are CCOs, compact central object, and rotating radio transients. And these are all basically different degrees of what happens to a neutron star, presumably in these supernova remnants. And we talked very briefly, mentioned this idea of millisecond pulsars, which we were thinking about if you had sort of a companion dumping material, you could spin up a dead pulsar and get these millisecond pulsars. So we spoke briefly about them. We won't say too much about them this time, but we will return to the idea of what happens to non-isolated neutron stars in the next lecture. And it's actually quite remarkable that there is such variation, because of course the story that we have for how we get neutron stars and this pulsating phenomenon is a fairly simplistic one. Not much is going on, so why do we end up with so much variation? And in particular, even if you think about the fact that we already saw that the properties of pulsars, basically everything was defined in terms of P and P dot. Why is there this broad range of objects that we can that are all really coming from this kind of P dot relation, and that are all really just neutron stars? And in fact, part of the answer is already in the question. We know that sort of the properties all depend on P dot, but we know there's quite a range of allowed values of P and P dot. We saw originally there's excluded regions, but in general you can have sort of a fair variety of combinations. But then those P and P dot describe a bunch of the other properties, like the age of the neutron star. This spin down luminosity you can actually show is computed in terms of just P dot on P cubed. That's one which we didn't explicitly go all the way through that calculation. And we also saw, right, that we can describe the magnetic field just in terms of P and P dot. And so, okay, if we have a range of P and P dot, well then, all right, now we're talking about looking at objects that have different ranges of ages, different ranges of magnetic fields. So now we begin to at least kind of think that maybe, yeah, there's hope for having quite a depth of variety in these objects. And indeed, the way that we represent that is by plotting their location in these p dot diagrams. And we find that each of these types of objects tends to inhabit a certain region of the p dot diagram. Now, there's also lines on here drawn for various ages and magnetic fields, right? That is coming from the fact that you can compute those two things in terms of p and p dot. And in the toot, we'll look more closely at exactly how those lines should go on this plot, etc., why they are the way they are. But for now, the relevant thing is that if you start plotting these objects and you classify them based on the properties which we're about to discuss, or the sort of features that we're about to discuss, you find that you create these little groupings naturally in this p dot diagram. And so the triangles represent our anomalous X-ray pulsars. The yellow ones do. The blue triangles are soft gamma repeaters, soft gamma ray repeaters rather. The red dots are the compact central objects. The purple squares are the rapidly rotating, the rotating radio transients. The isolated neutron stars are shown as little green squares. And then sort of the normal guys, the rotation powered pulsars, are all the little dots. So what's going on? Well, the normal pulsars, right, our radio pulsars, were simply these spin-powered or spin-down, right, giving rise to this energy loss. That energy was driving the pulsations, driving the wind, driving all of the properties. So it was this rotationally powered object, which had those nice regular pulses, had a pulsar wind nebula. They were, very ubiquitous. We knew many, many of these objects. And we did understand that some of them can be radio quiet. We, of course, also understand that if we're detecting, 2,000 pulsars, there's got to be more out there. So we're undersampling because if we're looking specifically for that beaming of the pulses, right, you need to have that nice line of sight down the cylinder that's swept out by the pole as it rotates, by the magnetic pole as it rotates around that rotation axis. But we've said plenty about them, so we won't say too much. And yeah, those guys inhabit this normal region, somewhere like 10 to the 11, 10 to the 13 is the range of their magnetic field. And they are sort of 100,000 to 10 million years old objects, and they seem to be this is the well understood group, or so forth, the well explained in terms of what we've talked about group. So what about the rest of these guys? Well, the other thing that we talked about was magnetite, right? And so if you had to venture a guess based on the fact that you've got the lines of the magnetic fields indicated here, what sort of objects do you think the magnetars are? So that's 10 to the 11th Gauss, increasing to 10 to the 12th for this line, 10 to the 13th, 10 to the 14th. What was the main thing about magnetars? Yeah, so they have high magnetic fields. So which of these objects look like it might be coming from that magnetar type group that we already talked about? Yeah, so the anomalous X-ray pulsars and the soft gamma ray repeaters are indeed these guys up here, which have sort of the longer periods, which is also something we mentioned for magnetars. They have the really strong magnetic fields, and they have now sort of these smaller, larger p dots. And so indeed, it turns out that those are the objects that we think of as magnetars, and they're just split into two categories. But they have some features in common, and then we'll look at why we split them into two groups. So the main thing with magnetars in general is that they do have this very high magnetic field, and in fact, it is the source of much of the emission from this pulsar, or from this magnetar rather than the rotation. In fact, so if you look, their luminosity is much higher than the E dot that you would compute based on just the spin down. So the energy is coming from the magnetic field, and it's giving rise to a lot of this emission. They have these larger periods, longer periods rather, and larger p dots, and they have those very, very strong magnetic fields. Of this group of AXPs and SGRs, something like 19 have been confirmed. They are, in general, fairly young, right? Because we did talk about they have this large p dot, so after a while you wouldn't really see them. They age, they disappear quickly in terms of having this period. So they are young objects if you're detecting them. They are very volatile, which kind of makes sense once we start thinking about exactly how we're getting the energy out of the magnetic field. We'll talk about that in just a few minutes. And in particular, they have these spectacular outbursts, which are going to be these giant flares, at least for the SGR group. So let's take a look at some of those features. So they all, in general, do have this large magnetic field, etc. So the generic magnetar properties. But what makes them separated out into two groups is that the soft gamma ray repeaters actually have these flare episodes, which result in soft gamma ray emission, bursts with peak luminosities of up to 10 to the 41 ergs per second. It's a very bright gamma ray flares, on top of the same sort of thing that anomalous X-ray pulsars have, which is a persistent luminosity in the X-rays with some sort of 5 times 10 to the 34 to up to 10 to the 36 ergs per second luminosities in that X-ray emission. The spin periods are all pretty comparable, although soft gamma ray repeaters have somewhat shorter sort of range of periods, 5 to 8 seconds, compared to the anomalous X-ray pulsars 6 to 12. They have similar sort of ages, on the order of 1,000 years, but again, the anomalous X-ray pulsars are sort of on the upper end of that. They're 3,000 all the way to even hundreds of thousands, so 400,000 years. And then sort of the breakdown of the objects for which we've confirmed that they are in this class, this range of properties. We have 7 soft gamma ray repeaters and 12 anomalous X-ray pulsars. But the overall similarities, including even in these, aside from really the only sort of obvious thing that jumps out at you as being different, is the presence of flares versus the absence of flares. Because those seconds, the periods are pretty much the same, the ages are of order the same sort of magnitude, so they are likely to be the same group or the same type of object, which we do think is just the magnetars. But so what could be kind of going on with these guys? So why could we get flares? In particular, when you have high magnetic field. Hey, what? Yeah. Right, so this is something we talked about briefly last time, or the time before. At some point we talked about it, that the same reason that you get solar flares from the sun, you can have these magnetic reconnection events. You've got these field lines, they're stretching out all over the place. They have quite a bit of tension in them as you try to drag everything in this co-rotating sense. And so, indeed, at some point, these magnetic field lines can just decide that it's time to give up. They snap, and then they close back on themselves. During that process, they release a lot of the energy that tension has built up. They also separate you possibly from the material through which you were, so the further material out from the star through which field lines were passing and being dragged. So you can separate from that and momentarily spin, maybe spin a little bit faster as you're no longer being dragged, that kind of thing. So that gets back to the glitch idea. But the main thing is we have these reconnection events that releases a tremendous amount of energy out of the magnetic field, and you can in fact get flares of material coming out and being released. So, and that sort of thing is what may be going on with causing these flares for the soft gamma ray repeaters. And in particular, if you think about where is the magnetic field sort of more likely going to experience a bunch of these things? Well, it's in the early life of the object where the magnetic field is still trying to settle into some sort of really stable configuration after having just compressed down to a neutron star. So it kind of, that story jives nicely with the fact that the soft gamma ray repeaters do seem to be the younger objects. And then sort of as you age, that behavior just kind of dies down, and you're left with an anomalous X-ray pulsar, perhaps. Okay. Now, beyond the sort of soft gamma bursts, what we also have are energetic giant flares, again presumably caused by that sort of thing. And the reason that you're forced to really think about it in terms of this magnetic reconnection event rather than some other scenario is that when you look at these guys, we don't see any evidence that they have any binary companions. So we're not thinking about some exotic interaction with a neighboring star. It has to be, coming from the pulsar or the magnetar itself. The persistence of the X-ray emission tells you that you do have a fair bit of magnetic field again driving this energy. And so if you've got that kind of energetic environment, you've got a strong magnetic field, this reconnection story seems likely. The sort of really nice feature, or one really nice feature of these giant flares in particular, is that they make it much easier in some sense to detect the period of these pulsations. So even if you don't have necessarily that alignment of the actual magnetic axis sweeping across you, you can still detect the pulsation in these tails, because the mechanism, which we won't go into, kind of couples that pulsation, that spin period, into the profile of that giant flare. And so you see here, you just look at time for your overall flare, you're counting the number of excess photons, or in case of looking at these gamma ray bursts, and you talk about your gamma ray photons as opposed to the X-ray photons. And what you do is you see the overall flare. There's this sharp peak, and then it kind of tapers back down to be quiet to sort of the normal levels. But as it does so, that period actually shows up as the tail tapers off. Okay? And so it provides a nice way of getting at the period of rotation of that object, even if you're not necessarily getting that beaming coming off of it. And then, looking at fine timing of the object between it can get you towards that measuring the spin down rate as well. And then you can go back. Now you've got period, you've got spin down. You can verify that you do indeed have large magnetic fields, estimate the age, all of that stuff. All right. So here are just some giant flares. 3 of these are sort of really definitely giant flares. One of them is not necessarily confirmed. There's a list here of the other soft gamma ray repeaters as well, but these 3 we have not detected any giant flares for. But these guys we have, and we had those nice structure profiles, so that helps us determine what's going on in terms of period and p dot. The same thing is also true for the sort of soft gamma ray bursts that are repetitive. They have that period imposed upon them. What do those soft gamma ray bursts look like? Well, they are fairly weak in terms of counts. The order is up to roughly almost 1,000, but really you're looking at order hundreds of counts. Those frequent bursts have luminosity, we said 10 to the 41 on the previous slide, certainly less than 10 to the 42 ergs per second, and they tend to be very short duration bursts, so less than a second. All of these seem to be about 0.2 of a second if you look at these plots, or less. So the widest ones are 0.2 of a second here. That one sort of tapering off. That one sort of a really long, weird shaped one. And these are really short. On the other hand, turns out there's sort of associated slightly higher energy, presumably, phenomenon, which result in more counts and a wider profile. The wider the profile, the more likely you are to get that period of rotation superimposed on your pulse. There is a very good example. It also should be noted that the duration of the pulse and also the shape depend on what energy photon you're looking at. So here we are looking 25 to 50. The pulse is sort of bimodal and lasts 4 seconds, whereas looking at this intermediate pulse in the range 40 to 70 keV gives you this nicely superimposed period of rotation on top of that feature. Right, these are all intermediate bursts, and they have durations of order a few seconds up to 40 seconds, depending on the energy you're looking at. So these are longer, and many more counts. You see these are order 10,000, even 100,000 counts. So these are more counts, more photons being emitted, longer duration events than whatever's causing the soft gamma ray bursts of intermediate, and probably, right, that builds up the scale to those 4 giant flares that we saw. And here is just an example of the giant flare again. You can get the period because it's very clear in this plot. You have several oscillations of it, since the giant flare lasts over 300 seconds. So you get very many samplings of that rotation period put in there. You can of course get the energy by talking about the fact that you know what energy you're measuring at, take the counts, integrate over this thing. The area under the curve basically should be the total energy, and then sort of divide by the amount of time that it took to emit it. So you have some 3 times 10 to the 44 ergs per second or so luminosity in this giant flare. So 1,000 times stronger than the regular frequent soft gamma ray bursts. But presumably the mechanism is sort of similar for all of them. Alright, so here are just some more samples of the normal bursts, again very short, etc. And it's kind of interesting to note that indeed that guy is an anomalous X-ray pulsar, but it has detected a weak burst. Alright, so there is a little bit of cross-mingling between these groups, or it's not a fine line between what you call an anomalous X-ray pulsar and an SGR, because even the AXPs can have sometimes, rarely, these bursts. Which is not surprising. They're all presumably a time evolution going from SGR into AXP, so there should be something that's kind of on the transition as you look. And there are some new candidates which have been found. It would be nice if these were included because they have been nicely identified with their supernova remnant, in which case, you know, we have independent measures of age and things like that, and so we can get better results or better confidence in all of our estimates of the properties of those objects. Alright, well the AXP, aside from the occasional pulse, are otherwise kind of boring objects because they're just sitting there. They have this nice uniform and fairly weak luminosity in the X-ray. They do not have optical companions, so we think they are isolated objects. They have these periods 5 to 10 seconds-ish, and they have a fairly constant spin down, but getting at that period is kind of difficult to do because they're not really pulsing unless you happen to be right on the beam. Right. Or if you get one of these nice soft gamma ray flares, then you have the opportunity perhaps to see the pulse period, or the rotation period in that signal, but being anomalous X-ray pulsars, not soft gamma ray repeaters, those kind of events are very rare for this group. For the anomalous X-ray pulsars, we have identified 12. Same old standard summary of their relationship. Yeah, no evidence for binary, so we've said all of that, and that's just a list. of 12 objects with these wonderful names that are obviously very creative and they roll right off the tongue. But that's what happens when you've got different catalogs. You just give a letter for the catalog and then an object number, because we've run out of names for things. I mean, let's face it, Uranus was almost going to be called George. So, you do know that, right? That's true.
What?
Uranus was almost called George, after King George, who funded the astronomer's work. And he was going to honor King George, but then people were like, come on, we've got like Mars, Venus, Mercury, George. I don't know. So luckily, we don't have George, but that would obviously end up being the name of stars and pulsars if we tried to give names to them all. So it's probably better that we have these crazy phone numbers instead of names. But, yeah. All right, back to the story of Magnetars. Yeah, George. Which obviously shows you it'd be good, right? Even in our world, we name stuff after people with lots of money, so that's how it worked back then. You either have to discover something, or you have to pay the person who discovered it, and then you can get your name on something. That's good. But anyway, the AXPs, I told you, they do have rare bursts. Actually, 7 of them, of those 12, have had detected bursts. So, again, that sort of reinforces the idea that they are very similar in nature, actually, to the SGRs, and it's just probably this time evolution kind of thing. And on the flip side of that, some SGRs do have quiescent periods in which they sort of stop having bursts. For instance, this one object has sort of been quiet since 1983. Okay, so we do have, again, this very tight sort of mixing of the properties between the two groups. Not really surprising, they inhabit more or less the same region of the PP dot diagram, and we have this idea that maybe it's this time evolution. All of this kind of supports that. So here's just some bursts, pulsating tails with the spin period put in it, and so you can separate out the gradual decay of the thing, and what you find is these nice pulses of the period, or in multiples of it. And so you can figure out, once you have these pulses, that's the best way of getting what's going on with the anomalous X-ray pulsar, unless it happened to actually be sort of a standard pulsar in the sense of being aligned with your line of sight and beaming at you with that lighthouse effect. All right. So, we do need to sort of complete the story. We started off with saying they're magnetars, but it would be nice to give a little bit more compelling evidence to that. And that just comes from the fact that we do need to sort of motivate them as neutron stars. The way it comes from is the fact that they do have the timing properties, i.e. some of them do pulse like normal, because we do have that fortuitous axis. We do see the glitches occurring, so we have this kind of behavior that's rather pulsar-like, which we know comes from the neutron star nature. We also know that at least 3 of the AXPs and 1/2 of our SGR sample have associated supernova remnants that we've identified them as belonging to. And so in that case, you know that they are in fact the remnants of the supernova explosion, which again suggests neutron star. Right, so then you're now sort of becoming more and more convinced. But there is that major difference that, unlike sort of the generic pulsar story that we were telling, where everything was rotation powered, the luminosity of these guys is much larger than that spin down energy. And so it is coming from this very strong magnetic field, which is consistent with them being younger overall. They have this longer period and larger spin down because of that very strong magnetic field. And that whole scenario with the higher magnetic field is consistent with this higher luminosity, because it's being driven by this kind of magnetic field decay, which it decays through those reconnection events, and just in general, as you sort of lose the dynamo through this backwards drag from the magnetic field lines that the dynamo was generating, which then pass through the slower, or wanting to be moving slower material outside the star. Okay, and then the pulse profiles for some of these beaming events tend to be these kind of weird shapes, which, you know, we talked about the fact that you get sort of actually a main peak and you get kind of an anti-peak when you sort of see the other pole, or when the other pole would be kind of facing you, because you get these sort of emissions from these regions still kind of coming towards you. So that's why you get this kind of weird asymmetric thing in the other pole. Then it finally properly leaves, and then you're back to the real pole coming and beaming at you, etc. And some of them just have the really nice normal sort of what you would really intuitively expect from a single, you know, pole beaming across you shape. It is worth mentioning that also, in accordance with our story of, you know, the kinds of emission that you get from a neutron star, that the neutron, the spectrum of these guys, at least from 0.5 to 10 kiloelectron volts, is well represented by a black body spectrum plus some power law spectrum. So, in this energy range, sort of what emission would kind of behave like a power law? Or put the question another way, since I'm telling you this is telling us about actual pulsar-like behavior of these objects, what other kind of emission did we say was the big feature in pulsars? Yeah, synchrotron. And indeed, it does look like a power law over much of the spectrum for synchrotron radiation, except for the actual me, kind of an increasing power law and a negative power law on the other side, and then there's that me where it bends over. So this is talking about, indeed, mixing black body and synchrotron. So that again is consistent with our story, that what we expect is indeed these guys are kind of the standard neutron star story, except that they are these magnetars with these really being blown from really massive stars, forming our neutron star, which then has a brief, less than 18 seconds worth of dynamo action, which can quickly ramp up the magnetic field, which is then flux frozen into the object. And you know, the sort of generic idea there is kind of similar to the formation of a pulsar, except that there we don't think we really get a dynamo. We're just kind of wrapping up and compressing the existing field lines at the time of formation. Alright, and indeed, again, as we started the discussion, the anomalous X-ray pulsars and the SGRs inhabit this high region, and you do see some overlap between where the yellow and the blue go, and that's also kind of consistent. There's more blue SGRs towards these younger age lines. So this is 1,000 years old, it's 100,000 years old. So you do see kind of a transition from blue to yellow, so to speak, in this diagram. So that's kind of the story there. So what about really bridging the gap between here and here? There are a few objects which aren't quite pulsars. Instead, they are high magnetic fields, but still rotationally powered objects. So we call them the high B rotation-powered pulsars. So they are really this kind of intermediate object between the standard pulsar and the magnetar. Here are some of their properties, you see, with this intermediate magnetic field. And they kind of have basically intermediate periods and p dots. The interesting thing about these guys is that they are all fairly close to us. For instance, this pulsar here is an X-ray pulsar. It has an associated supernova remnant. It's got a period of 0.3 seconds. Its magnetic field is 5 times 10 to the 13th Gauss. It turns out it's actually the youngest pulsar that we know of, just under 1,000 years old, and it does not have radio emission, but in general it's sort of this weird intermediate object. It has all the nice features, kind of a rotationally powered pulsar, aside from that radio emission. but it has also these kind of intermediate values for period, magnetic field, etc. And it's even more an intermediate than just the fact that it's period and magnetic field are intermediate between those classes. It basically has behavior from both types of objects as well. So we look at it, we see that in general it has the natural spin, rotation, powered features. So it has a luminosity consistent with its E dot kind of thing. But occasionally there are some magnetar-like X-ray bursts detected, and so we have this nice rotational powered thing, but superimposed on it, these bursts, which actually increase the flux by some 200 times, so a much dramatic increase in this, and there's an unprecedented in terms of how big in magnitude a glitch effect there is associated with this burst of flux. So there is evidence there that's telling us, because we did have this high B, right now that magnetic field has contributed something, given rise to this burst, done a little bit of a glitchy behavior, and so indeed it's intermediate in terms of also the sort of actual emission features that you get with it, not just in terms of period and the magnetic field. And most likely that's due basically to the fact that it does have that intermediate magnetic field, and so it's still kind of maybe representing settling of that magnetic field until it then turns into presumably a regular rotationally powered pulsar. And so that was the magnetar-like outbursts, and there are just some images showing you the increase in the brightness of that object. And so that's these guys pretty much over here. Now, what about the rest of these guys? So the green squares, was it? Yeah. No, the purple squares or pink squares. Here, the rapidly rotating or the rotating radio transients. What are they? Well, they're sort of bizarre in that they have these radio pulses, but they are sporadic. It is not every single rotation, presumably. Something is going on there. So what's going on? Well, we've got 12 of them that have these bizarre sort of things, not nice and periodic, not every interval. And they can even sort of switch off for any time between minutes to even hours. They have already even as sort of the most frequent period of pulsation, something of like 2 to 30 milliseconds, so they have longer periods than what we're considering for most pulsars. The period and magnetic field is higher than the rotationally powered. They're bright in the radio. Okay. They have X-ray properties which are like normal pulsars, but we generally actually only detect them after we have the pulses. So we're sort of selected in terms of looking for the pulses first. So we expect that these guys therefore are much more numerous than just the 12 that we know, and there should be a much more significant fraction of the population of that diagram, the PP dot diagram. But because we've selected and only looked for pulses, right, we're missing the ones that don't pulse towards us. Here is just one diagram of one such known object, and you can see it does have these sort of normal things. It kind of has like this nebular behavior, it has the sort of typical look to it as a regular pulsar, except that it's not pulsing every single time, and it has still this higher magnetic field, higher period. Along with those groups, or near them, are the INS group, which are the isolated neutron stars. So what are these guys? There's sort of 8 known, meaning 7 kind of confirmed and probably 1 more. They are all fairly nearby, less than 1 kiloparsec away. Their magnetic fields are again in this kind of intermediate range, 10 to the 13th Gauss. And the weird thing about them is that they have absolutely no radio emission again, kind of like those sporadic radio pulses from the rotating radio transients. And in this case, what are they? Well, they're probably actually really old pulsars. Right? And what's happened is that basically they've died, and so they no longer pulse, they no longer drive any nebulae. It is just this neutron star sitting out there and seemingly, isolated away from anything else. There's no wind nebula, nothing associated with it. And then we come to the sort of really kind of interesting object, which is sort of the opposite of those, which is that maybe we can actually form these neutron stars, and just initially somehow through their formation, either through the fact that the star that they formed from did not have much of a dynamo going on during its life ever, or that maybe these guys have really effectively shielded away the magnetic field, or the magnetic field was actually formed outside the core, and the core hadn't been penetrated by the magnetic field. Through whatever of those kind of reasons, this central compact object does not have a strong magnetic field. The reason we think that is because it has basically none of the normal features of any pulsar. It doesn't have the radio, no infrared, no optical counterpart, so it's not even really bright by itself. It has no nebula, it has no pulsing. But what we do see is a standard thermal blackbody X-ray spectrum suggesting it's cooling off. It is hot, it has a small radius, so that small radius is suggesting it is a neutron star. And an example is Cas A, which was imaged by Chandra for its first light experiment. And there is the object sitting at this center of the supernova remnant, so that's kind of nice. You figure that's the neutron star, but it's not doing anything in terms of pulsing or having its own nebula inside that supernova remnant. And really only 3 of them show any kind of pulsation, and they are, when you look at what kind of pulsation, or what that pulsation implies about the magnetic field, it's consistent with this idea that it has to be very weak, which is, in terms of looking at these guys, 10 to the 11th, that one is less than 10 to the 12th, so that's sort of a weak upper limit. And there's one example that is just 10 to the 10th. Right? So that's dramatically reduced compared to the typical pulsar story. So maybe these CCOs are basically the opposite of magnetars. Magnetars had that extra strong magnetic field. Maybe these guys have the extra weak. Right, and they are sort of in this region of the diagram, probably moving further down towards higher ages, so they could be also these more evolved objects as well. Alright, so that fills out what's going on in the PP diagram. Those guys are the millisecond pulsars, which is why we haven't talked about them. And it's interesting to note, really even by eye on this diagram, you see that there is sort of a region overall, a kind of line that fits or passes through all of these different classes. So there's this idea that maybe we can unify them, and in terms of how you do that, well, there's been efforts at understanding the physics of what's going on, and you could start to think about, if you put in a bit of physics, then what kind of temperatures and magnetic fields should be linked to each other because of the sort of movement that you expect at those temperatures, the sort of charges that you'd be liberating, what would be going on. So in particular, if you imagine how beta decay goes along, heats a crust, results in subsequent cooling of that crust, but the beta decay is delaying that cooling, which allows you to give the neutron star a sort of hotter temperature for delaying that cooling. Then, as long as you keep it warm, you also have this opportunity to kind of keep the magnetic field going. So if you kind of do that interplay, then you get this kind of prediction for temperature as a function of magnetic field, or effective temperature as a function of magnetic field. And you see these objects do kind of lie along that thing. So there's this coupling of the magnetic and thermal evolution that maybe describes exactly why we have this class of objects that obviously seem to sort of transition between each class, or at least link the classes together, and maybe it's coming from this kind of story. And that again is really just considering log of age versus log of b, which is sort of flipping pp dot, kind of inverting that diagram. They all sit in a certain region. That's the basic idea, is that since they do, they certainly maybe should have this common. And we already know that we're thinking of them all as neutron stars, so they do have a very common starting point. So maybe that's what's going on with those objects. All right, we'll stop here, have our 10-minute break, and then do a bit of a toot.